So for our final little section of our study of, functions, I have for you two functions right here. And we've talked about how they combine, we've talked about how we can compose them, we've talked about how to graph them. But now let's look a little bit at how they treat their range. We have two functions f and g, right? And they're both mapping between the same sets, right? The blue set and the red set. But the way that they do it are subtly different, okay? There's a property that f has that g doesn't, okay? And what I want to draw your attention to is this thing right here, okay? This is absolutely allowed, right? Totally allowed. You can have a function that maps two elements to the same element, but f doesn't do that, right? Let's assume that these are representative samples, right? F only ever maps one input to one output, right? Every output has a unique input, versus with the case of G, we don't have that, okay? And that turns out to actually be a really interesting and special property. So much so that it has a name, okay? So let's do our definition. So a function with domain A is called one-to-one, right? 1, 2, 1. Sometimes it's just written this way, right? 1-1. If no two elements share the same image, right? That is, right, in a little bit more, understandable terms, that is if, right, if say f of x1 equals f of x2, right? So say, the function value, is the same for x1 and x2, then that must mean that x1 equals x2, right? Um, there are other definitions that are totally equivalent, but this is the most useful one for us, okay? So let's take a look at the graph of some function and try to determine if it's one-to-one, right? See if there's some nice little test for us. Spoiler alert, there is, but we want to kind of discover it. Okay, so say we have some graph like this, okay? So if our graph was one-to-one, that would mean that whenever the function values are equal, the inputs to get those values are equal. But when does this happen, right? F of x1 equals f of x2 when we intersect the vertical line there, or the horizontal line there, right? So let's take some horizontal line and let's scan it through our function, right? Let's look at right there. Well, at this point, we have two intersections, right? Call that f of x1 and call this f of x2, okay? But we have that. This would be our x or our x2, and this would be x1, and they're not equal, right? So this function is not one-to-one, okay? It turns out, just like we had this handy vertical line test to tell whether or not a graph could be written as a function, we also have this horizontal line test to determine if a function is one-to-one, right? So let's formalize this, right? The horizontal line test says a function is one-to-one if and only if no horizontal line intersects the graph more than once, right? That was sort of what we did in the last little section with that graph, more than once. Okay, so let's do some examples, right? Let's just, I'll throw down a couple graphs here. Let's deal with, I don't know, how about 3 of them, right? Let's do 3 little examples, and we'll do the first 3 power functions, okay? Well, I guess we're going to start with the line, which is trivially a power function, right? So we'll do a line, we'll do a parabola, and we'll do a cubic, okay? Let's grab our horizontal line and ask ourselves if these are one-to-one. Well, as I scan my horizontal line across my function, we're only ever touching that function once, right? So is this one one-to-one? Yes. Okay. What about our parabola? Well, if I put it right there, well, you can see we have this horizontal line right here, which inputs or touches it at 2 distinct points. So no. Okay. What about on this cubic? Well, as I scan it up and down, it would seem to me like that's only ever going to touch once. So indeed, the cubic is one-to-one. Okay. So we looked at doing this graphically, right? But we can also do this algebraically, right? We have this categorization here, okay? So let's do an example with the algebra of it, right? So let's show that h of x equals 2x plus 1, or 2x plus 5 is 1-to-1, right? So what we need to do to show this, right? We need to show that h of x1 equaling h of x2 means or implies that x1 equals x2. And we can do that by just writing down a series of equalities that imply one another, right? So let's say h of x1 equals h of x2. Well, that would mean we can just plug that in here, right? That would mean that 2 times x1 plus 5, that's our definition of h of x1. And our definition of h of x2 is 2 times x2 plus 5, okay? So if these are equal, then I can subtract 5 from both sides to get an equivalent equation. And I get 2 times x1 is 2 times x2. Now if I divide both sides by 2, right, then I get that x1 equals x2. And indeed, the line 2x plus 5 is 1-to-1. So now what I want you to think about is, what does 1-to-oneness give us, right? Well, if we have our range, right, and we only hit that range or every point in that range once, then theoretically we could go back, right? If we have, let me go back to our first picture, right here, right? We have all of these maps here, right? If every point in this only gets hit once, right, because that's what 1-to-1 means, well, then we can go back, right? Versus here with this function, that's not 1-to-1. If we're trying to go back in the same way, right, well, where do you map 15, right? Because when we try to map 15 back, well, should 15 go to 2 or should 15 go to 3? If our map back is a function, it can only go to one of those, so we can't necessarily make heads or tails of it. Again, versus with these 1-to-oneness, we can come up with a notion of going back, right? Some sort of inverse function, right? Just like we have our, multiplicative inverses to undo multiplications, we have a, inverse function to undo our function. So let's write down our definition here. So let's say let f be a one-to-one function with domain A and range B. Okay? Then we can say its inverse function highlighting that, because sometimes I remember to highlight the words we're defining. Its inverse function, f inverse, well, it's going the other way, so it should have domain B and range A, okay? And it's defined by, say f inverse of y equals x if and only if f of x equals y, right? For any y in B, right? So as a picture, right, if we have some scribble amoeba set here and some amoeba set here, if f, say, takes x to y, right? So we'll change this color. If f takes x to y, well then f inverse will take y back to x, right? It will undo it, okay? Let's do quick examples of computing some things, right? So let's say we have the following tables of value, right? Say f is defined by, we have some inputs x, we'll say 2, 3, 5, 9, 11. See, at these values, we have f of x is, 1, 2, 6, 13, 12, okay? If you notice, this is one-to-one, right? Because there's no duplicates here. And we'll ask what is, say, the inverse at 2 and the inverse at 6. Well, to calculate the inverse at 2, we need to look at the range and see where we have 2, and then look at what maps to that. Well, 3 maps to 2, so the inverse function at 2 returns value 3. Same thing for f of 6, or f inverse of 6, right? We can look at where we map to 6 and look at what maps there. So it would look like to me that would be 5. We can also do the same thing graphically, okay? Say we have, some graph that looks like this. It hits the following points. It's there. We'll call this 1, 2, 3, 4. It hits there. It hits there. And it hits there, okay? And we'll connect it with a smooth curve like this, right? This is a function, right? It passes the horizontal line test, right? Pick any horizontal line here. It's only going to cross it once, okay? And let's look for, let's look for f inverse of 1, f inverse of 2, and f inverse of 3, okay? Or I guess I'll label these 1, 2, and 3 for completeness, okay? So f inverse of 1, well, what I can do is I can start at 1, and I can go on over to the graph, and then walk down and see what input sent to the output 1. Well, that would look to me like the input that sends to 1 is 1, okay? So now we're asking what input sends to the output 2. So we go to our output 2 and we trace over, hit the graph and trace down, and it would look like we have 3. We'll color code that correctly. And what about 3, right? What input sends to the output 3? That would look to me like 4. We know that sort of by construction, right, the inverse and the original function sort of undo each other, right? And we'll go over how to compute the inverse function in a bit. But before we get there, right, can we come up with some sort of test, right? Is there some way, given two functions, to test if they're inverses of each other? That's going to be the inverse function property. That's going to allow us to do that, okay? So the inverse function property, okay? So we'll need a function. F is 1 to 1 with domain A and range B, okay? Then F inverse has the following properties. So 1, if we take F inverse of F of X, right? So first we apply F, and then we apply F inverse. Well, that should just give us X for any X in my domain. Similarly, if we apply F to the inverse of some element Y, well, we should spit out Y back, right? This is what it means for our functions to undo each other, okay? So we'll do one quick example of this, right? And then we'll look at how to compute them, okay? So let's say to show, I don't know, F of X is X cubed, and G of X equals X to the 1/3 are inverses, okay? So what we need to do is we need to compose these both ways and show that the only thing that we're left with is X, okay? So let's do that. So we have F of G of X. It's going to be F of X to the 1/3, which means we're doing X to the 1/3 cubed. If you remember your exponent rules, we're going to multiply down that 3, right? And so that means we're going to have X to the 3/3, or X. Now let's go the other way. We have G of F of X, which is going to be G of X cubed. So we're looking at X cubed to the 1/3. But by the same reasoning as before, right, we're going to multiply that 1/3 times 3 and just end up with X to the 1. So we have checked it, right? We've checked that our solution holds. Okay. So now, of course, the infamous question is, how do we find them, right? And there's a sort of like heuristic. There's going to be 3 examples for how to do it, and hopefully you'll get a good idea of how we can compute inverses, okay? Our first one, say we're going to look for the inverse of 3x minus 2, right? This is a one-to-one function. For all of these, I'm going to assume that these are one-to-one because they are, right? You wouldn't be able to calculate the inverse if you weren't one-to-one. You'd run into some sort of problems somewhere along the line. But to calculate this inverse, the first thing we're going to do is write this as an equation. So y equals my function of x. And now we're going to try and solve this equation for x, okay? I can add 2 to both sides. and then I can divide by 1/3, and I'll get x, or I'll divide by 3, multiplying by 1/3. We'll get 1/3 x minus 2/3, or 1/3 y minus 2/3. But now, funnily enough, if everywhere I see an x, I write a y, and everywhere I write a y, I see an x, okay, we'll get now the equation y equals 1/3 x minus 2/3, and this is indeed the inverse function of f. I'm going to leave it for you to compose these. Definitely pause it, take a second to confirm this on your own, and we're going to move on to the next one, right? Try and squeeze this onto this page, right? Let's say b, we have, say, g of x is x to the 5th minus 3 over 2. Okay. Well, let's write this as an equation, right? Y equals 1/2 x to the 5th minus 3/2. So if we're attempting to solve for y, we can move that over and we'll get y minus 3/2 is 1/2 x to the 5th, which means that x to the 5th is 2y minus 3/2, or minus 3 actually. But now if we take fifth roots, right, because it's an odd root, we don't pick up a plus or minus, so we're totally good there. So we get x is the 5th root of 2y minus 3. But now we've done it, right? Now that we've solved for x, we can switch our x's and y's to get y is the 5th root of 2x minus 3, which is indeed the inverse function. Once again, check that on your own. The final one that we'll do before we wrap up this section and this chapter is one that's a bit more complicated. Let's say 2x plus 3 over x minus 1. Later in the quarter, we're actually going to learn how to graph stuff like this. It's going to be really interesting. But for now, we'll just look at this and attempt to find its inverse. So as we've said, just sort of following these steps, right, we're going to set y equal to 2x plus 3 over x minus 1. Now we're going to cross multiply in order to get rid of our fractions. So we're going to have yx minus y equals 2x plus 3. Rearranging this a little bit, right, kind of moving things over. Looks like we're going to get yx minus 2x equals 3 plus y, right? I can factor an x out of this side, right? And that's going to give me x times y minus 2 equals y plus 3. But now if I divide both sides by y minus 2, well, then I'll get x by its lonesome, right? We'll get x is y plus 3 over y minus 2. Switching our x's and y's, we see that y is x plus 3 over x minus 2, which is indeed, as we call this f, the inverse function of this guy up here. Once again, definitely check and verify that this is the inverse function, that the inverse that the inverse function property holds for these two guys. And with that, we have wrapped up the chapters.